Welcome to Episode 92, APIs and FHIR Requirements Impact, where we explore how the rise of healthcare interfaces reshapes compliance expectations under the R2 framework. Application programming interfaces, and especially those built on the Fast Healthcare Interoperability Resources Standard, expand both transparency and exposure. They empower patients and partners to access data efficiently, yet they also pull multiple control domains into direct interaction. Authentication, transmission security, consent management, and logging once lived inside data centers. Now they sit at the boundary between systems and external apps. Understanding how APIs intersect with R2 requirements ensures that organizations modernizing for interoperability preserve rather than weaken assurance. The challenge is not only technical but organizational, aligning governance and engineering to the same precision. APIs touch dozens of control requirements across privacy, security, and operational domains. In R2, that means policies and evidence must extend into the application interface layer, not just infrastructure. For example, access control, encryption, audit logging, and incident response all gain new dimensions when exposed through APIs. Each FHIR endpoint essentially becomes a living control implementation, executing policy in real time. An organization might meet encryption requirements through database safeguards, yet still fail compliance if API responses transmit data without proper channel protection. Recognizing that APIs are not add-ons but functional extensions of governance helps prevent gaps. Controls must cover every digital doorway that data passes through, no matter how modern the interface. Identity, authentication, and authorization controls form the first compliance intersection point. R2 clauses addressing user identity, multi-factor authentication, and access review apply fully to API consumers and system accounts. OAuth 2.0 and OpenID Connect protocols provide technical enforcement, but organizations must still document who can issue tokens, how scopes are approved, and how revocation occurs. For instance, if a patient portal allows mobile apps to connect via delegated access, each app must authenticate securely under least privilege. Evidence may include screenshots of token policies, key rotation logs, and access review results. The essence of compliance remains the same, only the interface changes. Properly governed identity layers turn abstract assurance into verifiable control. Logging and auditing requirements take on new meaning in the FHIR context. APIs multiply event volume dramatically, capturing not only login attempts, but every query, read, or update request. R2 expects organizations to show that these records are complete, time-stamped, tamper-resistant, and tied to identity. For example, a clinician retrieving lab data through an API should generate an audit entry equivalent to an EHR access log. Centralizing these logs into a unified monitoring platform allows analysts to correlate activity across systems. Assessors often check whether API audit trails feed incident detection pipelines and whether retention matches regulatory timelines. Effective logging turns interoperability into visibility, transforming potential chaos into controlled traceability. Data minimization and disclosure restrictions reinforce privacy within API ecosystems. FHIR endpoints should return only the information necessary for the request's purpose, applying filters and resource-level constraints. Overly broad responses violate the principle of least disclosure and can expose unrelated patient details. For example, an app fetching immunization data should not receive demographic fields unnecessary for its function. Compliance with R2's data protection requirements demands that these filters be documented and tested. Developers must understand that privacy is not optional metadata. It is an enforced rule of design. Minimization proves that access convenience and confidentiality can coexist under disciplined architecture. Consent, purpose, and legal bases align the technical access flow with regulatory expectations. Each API call implicitly asserts a purpose: treatment, payment, operations, or patient-directed use. Systems must record these purposes and verify appropriate consent before releasing data. Under R2 and HIPAA, an organization must demonstrate how consent status influences system behavior, whether through pre-query checks, token scopes, or internal policy mappings. For instance, if a patient withdraws consent, future API tokens linked to that individual must fail authorization. Evidence may include consent logs, policy statements, and automated enforcement scripts. Linking legal purpose to technical execution transforms abstract privacy principles into measurable operational control. Transmission security and channel protections ensure that data in motion remains confidential and unaltered. All API communications should use TLS 1.2 or higher with modern cipher suites and certificate validation. Mutual authentication may apply for system-to-system connections. Documentation must show how encryption keys are managed and rotated and how weak protocols are disabled. For example, assessors may review firewall configurations and packet capture evidence verifying encrypted flows. In R2, transmission security maps directly to requirements for encryption in transit and network monitoring. APIs amplify the need for rigor, as every new endpoint represents another path where security must be absolute. Channel protection becomes both a compliance proof point and a frontline defense. Retention, deletion, and record-keeping controls govern how long API-related data persists. Logs, cached responses, and temporary tokens must follow the same retention schedules as other system artifacts. Organizations often overlook transient data, such as session caches or staging exports, which can violate retention or disposal policies if unmanaged. For instance, sandbox environments used for FHIR testing must not store live patient identifiers beyond approved durations. Under R2, evidence includes documented retention tables, deletion scripts, and verification reports. Applying lifecycle management uniformly across API-generated artifacts ensures consistency and compliance from creation through disposal. Third-party access and vetting requirements elevate external risk management to a new level. Many FHIR implementations allow patient-directed apps or partner systems to connect directly. Each third party becomes an extension of the data environment. R2 requires risk assessments, security reviews, and agreements that mirror business associate obligations. For example, verifying that a third-party app encrypts stored data or supports token revocation demonstrates due diligence. Vetting may also include developer registration and periodic reassessment. By managing external actors as governed participants rather than passive consumers, organizations maintain compliance while fostering interoperability safely. Contracts, business associate agreements, and related obligations formalize legal accountability for data handled through APIs. These documents must define responsibilities for security, breach notification, and permitted uses of PHI. When multiple vendors interact, such as a SaaS EHR integrating with payer systems, the BAA must reflect every interface where data flows. Under R2, assessors review signed agreements and confirm they correspond to actual system relationships. Evidence might include contract repositories, signature logs, and renewal tracking reports. Sound contractual governance ensures that assurance extends beyond technology to the legal frameworks that underpin shared trust in the healthcare ecosystem. Incident detection and notification clocks apply equally to API-driven systems. Because data exchanges real-time, breaches can propagate rapidly if unnoticed. Monitoring tools must detect abnormal access, repeated failed calls, or data volume anomalies. Once identified, notification deadlines, whether HIPAA's 60-day limit or stricter internal policy, must be met. Demonstrating compliance requires documented escalation procedures and historical incident timelines. For example, a breach simulation might test how quickly an exposed API key is revoked and stakeholders informed. R2's integration of detection, response, and notification expectations ensures that technical speed does not outrun accountability. Evidence mapping for API scenarios ties all these threads together. Each R2 requirement must point to tangible artifacts, access control configurations, encryption screenshots, consent logs, or incident reports. Mapping creates a clear trail from requirement to proof, making assessments efficient and defensible. For example, the same OAuth configuration file may satisfy multiple requirements: authentication, key management, and token lifecycle if referenced correctly. Mature organizations maintain evidence catalogs organized by control domain, updated automatically through compliance tooling. Evidence mapping transforms sprawling API ecosystems into organized assurance environments where every claim links directly to verifiable documentation.
Common pitfalls in API compliance often stem from scope ambiguity or inconsistent ownership. Security teams may assume developers manage configuration, while developers assume compliance handles oversight. This disconnect leaves controls incomplete. Other pitfalls include untested consent revocation, overly broad data sharing, or missing audit retention for API logs. Corrective measures start with cross-functional alignment, defining roles, establishing secure defaults, and automating verification. Periodic internal audits catch drift before assessors do. The goal is to build predictability into governance. Every API behaves as expected, every safeguard operates as declared, and no compliance element is left implied.